Sure. Am I ever anywhere?
Yeah. Hey, you have the same Zoom background as me.
It's amazing.
Yeah, it's weird.
I'm actually right across the street. I'm at the residence inn.
Yeah.
So, you know.
Okay,
All
so
right.
why don't you let her rip, Noah?
Well, watch what you wish for. Okay, thanks very much, Paul. As I talked about earlier on today in our little wrap up of the first part of the morning, remote sensing data, particularly the data we get from the LRO spacecraft, is incredibly useful for untangling the complex history of the Apollo 17 landing site, and specifically for ANXA, the deep drill, the drive tube 73001 and 02. The image on the screen here is a oblique high sun view from the LRO camera, narrow angle camera instrument, and provides a wonderful context and a good reminder that we're really dealing with a complicated landing site, almost as complicated as Clive and Paul Lucy. Next slide, please.
Famous delayed arrow keys. Mouse, okay.
So we'll be able to zoom in on this image later on. So for all of eternity, Paul and myself have been showing remote sensing data in this view, the nadir map view looking straight down. And for 80% of the moon, this is probably a totally appropriate and applicable way to convey the glory of remote sensing data. And you'll see in Dan Moriarty's presentation later this week, really the value of putting the mapped data into 3 dimensions, especially when you're dealing with such a dynamic area as the Taurus Littrow Valley. This Alrock NAC view at the left, it's about, or left on my screen anyway, is about 10 kilometers across, and it highlights some of the real subtle variations we've seen in what had historically been described as a single light mantle deposit. And you'll see through the remote sensing data that I'm going to show you here, that interpretation, the historic interpretation, certainly needs to be revisited, and particularly when we consider the implications for this core tube. Next slide, please. Okay, so again, we are so lucky to be able to study Apollo 17. It was the most complex, both technically and geologically, of the Apollo landing sites. It demands that we study it in 3 dimensions. And this zoomed in view on the valley, you start to really appreciate the complex nature of the South Massif, the potential landslide or landslide deposits, and its relationship with the floor. At the center of the image, and in a moment, I'll put on a marker that shows where Station 3 is. Its very location is very complicated in relationship to the Lee Lincoln Scarp, the Light Mantle Deposit, Lara Crater, and several nearby craters. Of course, I'm not the first person who's thought about the 3-dimensional nature of the valley. In a paper in 2002, Mark Robinson and Brad Jolliffe used the then best available topography to correct Clementine data to start teasing out some of the spectral signatures along the massifs. Of course, we can do the same thing with modern data sets and really begin to unravel the history of the valley, particularly the Station 3 site. Let's go to the next slide, please. Okay, one of the great tools that we have at our fingertips now is QuickMap. This is an analytical website, basically hosted by the LRO camera team, that allows us to interrogate LRO data and other data sets in 3 dimensions. And so in this very slow fly around, hopefully you begin to not only see the capabilities of putting data into this 3-dimensional nature, but again, the intricacies of what we see at the South Massif. We don't just see a single avalanche deposit coming off the South Massif. We see dark and light streaks, and Dan will get into the compositional implications for those features, and indeed the relationship of the albedo patterns in the South Massif compared to what we see on the light mantle is complicated, to say the least. Just as a point of reference, the South Massif rises about 2.3 kilometers over the valley floor. And Station 3 is about itself 2.2 kilometers away from the base of the South Massif. So we're talking about some fairly substantial distances, both in height and in length. Next slide, please. Okay, so again, here's that famous oblique view I was showing earlier on. One of the favorite things I noticed in this image, not only is that this light mantle deposit has a darker, a lighter, and a brighter component to it, but also the blast zone around the Apollo 17 lunar module is quite visible. And I don't know if Paul's going to point to it here. Yeah, close enough, Paul. This is good.
There you
Tested it right there. Exactly. And so, very subtle albedo changes become quite apparent in this view. And so, one is immediately drawn to the darker boulders along the South Massif, the summit of the South Massif, as well as, of course, the material streaking down. Let's take another view. Next slide. And there's station 3 marked right there at the rim of Lara crater along the surface expression of the Lee Lincoln Scarp itself, a very complicated environment, which we'll get into in a moment. Next slide, please. Thanks, Paul. As a reminder, we can use different types of remote sensing data to probe the nature of the regolith. This figure from Becky Gent highlights some of the different probing depths. Of course, optical images go up over measure the upper few microns of the surface. The thermal data, which I'll show in a moment, probes upper 5 to 10 centimeters, radar data up to 1 meter. So if we combine all of those data sets together, we can get a 3-dimensional view of the Taurus Littrow Valley. And then again, combined with the actual 3-dimensional view of the Station 3 site from the core, trying to connect the two, I think, can help advance our understanding of the complex history of Valley. Next slide. Okay, so this is that same high sun view now projected in QuickMap. So this is data projected on top of a 3-dimensional model. Station 3 is circled in blue at the very middle of the scene there. And immediately what is obvious is that we have, if you go to the next slide, a few different features along the South Massif. Thanks. Oh, back one. Itchy trigger finger, Paul. So first of all, at the Coast Bar meeting a few months ago, Robinson and Jolliffe hypothesized that there's some of the features on the South Massif could be secondary craters from Tycho. And you'll notice that there are indeed bright albedo patterns emanating from what could be considered source craters. However, those rays coming from those source craters not only, of course, are affected by topography, but by the change in slope when you go from the South Massif to the valley floor. Whether or not all of the albedo patterns we see associated with the light mantle deposits could be connected to that particular set of secondaries remains to be seen. As you saw in Jack's presentation earlier on today, he has potential ages for the young light mantle and the older light mantle deposit. Whether or not those ages reflect Tycho still remains to be seen. But again, this is a complicated site, and we can only really begin to now unravel it thanks to the samples and the remote sensing data. Next slide, please, Paul. This is Paul Lucy's map, so he can take credit for its real magnificence in synthesizing the optical maturity of the region. Paul's student Miriam Lenneman in 2009 used Kaguya data to come up with a updated optical maturity map. And what you can barely begin to make out is that indeed those two light mantle deposits indeed have differences in optical maturity values relative to the valley floor. If you assume the valley floor has effectively 0 maturity, we have about a 20% maturity factor for the young light mantle and about 10% for the old light mantle. And I think I mapped those two out in a moment here. And so clearly the remote sensing data is telling us, it's screaming at us that there are differences, and whether or not we see those differences in the light mantle, in the core sample, excuse me, remains to be seen. Let's go to the next slide, please. Nope. Yes, Paul. So again, here's at least the two light mantle deposits that were mapped by Schmidt et al. In 2017, the larger young light mantle deposit, which we sort of associate with the avalanche or the assumed avalanche deposit, and the old light mantle. In 1972 in Apollo 17, those were mapped as single units. Largely, the only reason they were mapped as single units was because we only had effectively high resolution images from Apollo 15 at low sun angle, and the albedo differences were just not pronounced. So it was assumed that they were a single related unit. Again, now our interpretation has evolved, and the causes of these light mantle, these avalanche deposits, these light mantle deposits, is still for debate. And again, potentially Jack's sense interpretation of their ages could help us inform potential causes, whether it's related to Tycho, other cratering, or movement along the scarp. Next slide, please. Getting into thermophysical data, Diviner gives us an opportunity to probe the upper few centimeters of the regolith, and looking at the H parameter derived by Paul Hayne in 2017 allows us to see that indeed the area around the light mantle, and you'll see the circle, the blue circle, the location of the Station 3, is effectively indistinguishable from the surrounding regolith. The nature of the light mantle deposits really doesn't come through. This tells me that effectively that enough weathering has occurred, enough mixing of the regolith has occurred to effectively homogenize the regolith light mantle, old light mantle, or across the valley floor. This is helpful in interpreting not only the age, but again, the processes that are going on. And as Dick Morris will show, potentially, we see changes in the surface maturity over the upper few centimeters of the Station 3 core sample, indicating that, yes, typical regolith mixing processes have occurred. And so effectively, the homogenization at this depth appears to be fairly uniform across the valley floor. But if we go to the next slide, Paul, we return to our sort of notional low sun angle view, which is, again, maybe the traditional view of the Taurus Littoral Valley, certainly is what informed the pre-mission planning for Apollo 17. And again, a reminder that we're dealing with a site at Station 3 that's on the face of this 100-meter high fault scarp, effectively, that there's real topography going on at Station 3 and almost certainly influence the emplacement of an avalanche deposit. Let's go to the next slide. But again, we don't see, in at least the remote sensing data, variations across that deposit. And so finally, what we have here is radar data from mini-RF. And again, this is probing regolith differences over the upper meter or so. One interpretation in the variations that we see across the valley is that there's a difference in near surface or subsurface scatter, small rocks. And again, what we'll see in the interpretation of the Station 3 core is that we do indeed see small rock fragments at depth within the core sample. Now, how uniform that is across the light mantle deposit, well, we don't have the core samples across the deposit to tell. But what we do have is this data suggesting that across the entirety of at least the young light mantle deposit, there is some fairly uniform subsurface property. Again, below 5 centimeters, but in the upper meter, that is uniform. It doesn't peter out as you go away from the bottom of the South Massif. It is something that's ubiquitous across the entirety of this massive deposit. And so what formation process could account for this really uniform? There's no fading as you get further and further away from the foot of the South Massif. And I think that's an interesting implication for thinking about the dynamics of the emplacement of this
2 minutes,
avalanche
Noah,
deposit.
2 minutes.
Oh,
2
okay,
minutes.
plenty of time then. All right, deep breath. One more slide to go, Paul. So what does it all mean? Well, I haven't answered anything. I've raised more questions, but I think the interpretation of the remote sensing data in light of what we have from the core sample can help us begin to disentangle what we see here in what is a very, very complicated regolith story. Again, we have this wonderful three-dimensional landing site. The Apollo 17 region is incredibly complicated, both in terms of regolith dynamics, volcanic history, impact history, all recorded there. We have the benefit of having a very robust remote sensing data set that allows us to begin to pull at some of those threads. Now, as we talked about at the end of this morning's session, and I'll reiterate here, the Artemis sites may not be as geologically complicated as Apollo 17, but many of the regions that we've released as potential Artemis 3 landing sites are going to be at the summits of effectively massifs. And so our interpretation of the history of what's happened here may certainly help inform some of the processes that we'll be seeing from a different vantage point for Artemis 3 and subsequent Artemis missions. And I think with that, I'll pause and we can move on to the next speaker. Thank you.